Elixir School, OTP distribution. Introduction to distribution. We can run our Elixir apps on a set of different nodes distributed across a single host or across multiple hosts. Elixir allows us to communicate across these nodes via a few different mechanisms, which we will outline in this lesson. Communication between nodes. Elixir runs on the Erlang VM, which means it has access to Erlang's powerful distribution functionality. A distributed Erlang system consists of a number of Erlang runtime systems communicating with each other. Each runtime system is called a node. A node is any Erlang runtime system that has been given a name. We can start a node by opening up an IEX session and naming it. IEX s name Alex at localhost. Let's open up another node in another terminal window. IEX s name Kate at localhost. These two nodes can send messages to one another using node.spawnLink, communicating with node spawnLink 1. This function takes two arguments: the name of the node to which we want to connect, and the function to be executed by the remote process running on that node. It establishes the connection to the remote node and executes the given function on that node, returning the PID of the linked process. Let's define a module, Kate, in the Kate node that knows how to introduce Kate, the person. Sending messages. Now we can use node spawnLink 2 to have the Alex node ask the Kate node to call the sayName function. Node, this is in the Alex node. Node spawnLink Kate at localhost. Erlang Kate at localhost. Then the function Kate sayName. A note on I/O and nodes. Notice that although Kate sayName 0 is getting executed on the remote node, it is the local or calling node that receives the I/O puts output. That is because the local node is the group leader. The Erlang VM manages I/O via processes. This allows us to execute I/O tasks like I/O puts across distributed nodes. These distributed processes are managed by the I/O process group leader. The group leader is always the node that spawns the process. So since our Alex node is the one from which we called spawnLink 2, that node is the group leader, and the output of IO.puts will be directed to the standard output stream of that node. Responding to messages. What if we want the node that receives the message to send some response back to the sender? We can use a simple receive1 and send2 setup to accomplish exactly that. We'll have our Alex node spawn a link to the Kate node and give the Kate node an anonymous function to execute. That anonymous function will listen for the receipt of a particular tuple describing a message and the PID of the Alex node. It will respond to that message by sending back a message to the PID of the Alex node. head equals node spawn link to Kate at localhost. Flush. A note on communicating between nodes on different networks. If you want to send messages between nodes on different networks, we need to start the named nodes with a shared cookie. IEX, sname, Alex at localhost, cookie, secret token. Only nodes started with the same cookie will be able to successfully connect to one another. Node spawn link 2 limitations. While node spawn link 2 illustrates the relationships between nodes and the manner in which we can send messages between them, it is not really the right choice for an application that runs across distributed nodes. Node spawn link 2 spawns processes in isolation, i.e., processes that are not supervised. If only there was a way to spawn supervised asynchronous processes across nodes. Distributed tasks. Distributed tasks allow us to spawn supervised tasks across nodes. We'll build a simple supervisor application that leverages distributed tasks to allow users to chat with one another via an IEX session across distributed nodes. Defining this supervisor application. Generate your app. Mix, new, chat, the supervisor flag. Adding the task supervisor to the supervision tree. A task supervisor dynamically supervises tasks. It is started with no children, often under a supervisor of its own, and can be used later on to supervise any number of tasks. We'll add a task supervisor to our app's supervision tree and name it Chat Task Supervisor. Def module, chat application to use application. Then we have a start and the children task supervisor. We give it a name, chat.taskSupervisor. We have options 1 for 1. Now we know that wherever our application is started on a given node, the chat supervisor is running and ready to supervise tasks. Sending messages with supervised tasks. We'll start supervised tasks with the task supervisor async 5 function. This function must take in 4 arguments. The supervisor we want to supervise the task, so this function must take in 4 arguments. The supervisor we want to use to supervise the task, this can be passed in as a tuple, i.e. supervisor name, remote node name, in order to supervise the task on the remote node. Second argument, the name of the module on which we want to execute a function. Third argument, the name of the function we want to execute. Fourth argument, any arguments that need to be supplied to that function. You can pass a 5th optional argument describing shutdown options. We won't worry about that here. Our chat application is pretty simple. It sends messages to remote nodes, and remote nodes respond to those messages by IO putsing them out to the standard out of the remote node. First, let's define a function, chat receive message 1, that we want our task to execute on a remote node. def module chat, def receive message. We just puts it. Next up, let's teach the chat module how to send the message to a remote node using a supervised task. We'll define a method, chat send a message to, that will enact this process. Def send message, recipient message, do spawn task to the module, receive message, recipient message. Let's see it in action. In one terminal window, start up our chat app in a named IEX session. IEX sname alex at localhost capital X mix. Open up another terminal window to start the app on a different named node, Kate at localhost. Now, from the Alex node, we can send a message to the Kate node. Chat send message Kate at localhost hi. Switch to the Kate window and you should see the message. The Kate node can respond back to the Alex node. Chat send message Alex at localhost hi, or how are you? And it will show up in the Alex node's IEX session. Let's revisit our code and break down what's happening here. We have a function chat send message to that takes in the name of the remote node on which we want to run our supervised tasks and the message we want to send that node. That function calls our spawn task for function, which starts an async task running on the remote node with a given name, supervised by the chat task supervisor on that remote node. We know that the task supervisor with the name chat task supervisor is running on that node because that node is also running an instance of our chat application, and the chat task supervisor is started up as part of the chat app's supervision tree. We are telling the chat task supervisor to supervise a task that executes the chat receive message function with an argument of whatever message was passed down to spawn task for from send message to. So chat receive message hi is called on the remote Kate node, causing the message hi to be put out to that node's standard out stream. In this case, since the task is being supervised on the remote node, that node is the group manager for this I/O process. Responding to messages from remote nodes. Let's make our chat app a little smarter. So far, any number of users can run the application in a named IEX session and start chatting. But let's say that there is a medium-sized white dog named Moby who doesn't want to be left out. Moby wants to be included in the chat app, but sadly he does not know how to type because he is a dog. So we'll teach our chat module to respond to any messages sent to a node named Moby at localhost on Moby's behalf. No matter what you say to Moby, he will respond with chicken, because his one true desire is to eat chicken. We'll define another version of our send a message to function that pattern matches on the recipient argument. If the recipient is Moby at localhost, we will grab the name of the current node using node.self and give the name of the current node, i.e. the sender, to a new function, receive message from Moby to so that we can send a message back to that node. Send message. Moby at localhost message. We have a spawn task of the current module. Receive message from Moby at localhost message, and node.self. Next up, we'll define a function receive message for Moby 2 that IO puts out the message in the Moby node's standard out stream and sends a message back to the sender. Def receive message for Moby message from. We IO puts the message, and then we send message from chicken. By calling send message to with the name of the node that sent the original message, the sender node, we are telling the remote node to spawn an supervised task back on that sender node. Let's see it in action. In 3 different terminal windows, open 3 different named nodes: Alex, Kate, and Moby. Let's have Alex send a message to Moby. Chat, send message, Moby at localhost, hi, chicken? We can see that the Alex node receives the response, chicken. If we open up the Kate node, we'll see that no message was received, since neither Alex nor Moby sent her one. Sorry, Kate. And if we open the Moby node terminal, and if we open the Moby node's terminal window, we'll see the message that the Alex node sent. Hi. Testing distributed code. Let's start by writing a simple test for our send message function. Def module chat test use xunit case async true. We have a doc test for chat, and then our test for send message is assert chat.sendMessage Moby at localhost hi returns OK. If we run our tests via mix test, we will see it failing with the following error. No connection to Moby at localhost. This error makes perfect sense. We cannot connect to a node named Moby at localhost because there is no such node running. We can get this test passing by performing a few steps. First, open up terminal window and run the named node, i.e. we make a Moby IEX session. Then run the tests in the first terminal via a no-named node that runs the mix tests in an IEX session. This is a lot of work and definitely wouldn't be considered an automated testing process. There are 2 different approaches we could take here. 1. Conditionally exclude tests that need distributed nodes if the necessary node is not running. 2. Configure our application to avoid spawning tasks on remote nodes in the test environment. Let's take a look at the first approach. Conditionally excluding tests with tags. We'll add an xunit tag to this test. Tag distributed. And we'll add some conditional logic in our test helper to exclude tests with such tags if the tests are not running on a named node. Exclude if node alive, else distributed true. Xunit start exclude. We'll check to see if the node is alive. We check to see if the node is alive, i.e. if the node is part of a distributed system with node alive. If not, we can tell xunit to skip any tests with the distributed true tag. Otherwise, we will tell it not to exclude any tests. Now, if we run plain old mix tests we'll see one excluding tags distributed true and one test excluded. And if we want to run our distributed tests, we simply need to go through the steps outlined in the previous section, run the mobi at localhost node, and run the tests in a named node via IEX. Let's take a look at our other testing approach, configuring the application to behave differently in different environments. Environment-specific application configuration. The part of our code that tells Task Supervisor to start a supervised task on a remote node is here. Task Supervisor async 5 takes in a first argument of the supervisor we want to use. If we pass in a tuple supervisor name location, it will start up the given supervisor on the given remote node. However, if we pass task supervisor a first argument of a supervisor name along, it will use the supervisor to supervise the task locally. Let's make the remote supervisor 1 function configurable based on environment. In the development environment, it will return chat.taskSupervisor recipient, and in the task environment, it will return chat.taskSupervisor. We'll do this via application variables. Create a file, config dev.exs, and add use mixconfig, config chat remote supervisor, a function recipient. And then another config file with config test exs, and the remote supervisor here will only return chat task supervisor. Remember to uncomment this line. In config exe. Import config mixenv.exs. Lastly, we'll update our chat remote supervisor 1 function to look up and use the function stored in our new application variable. defp remote supervisor recipient to application.getenv chat remote supervisor recipient. Conclusion. Elixir's native distribution capabilities, which it has thanks to the power of the Erlang VM, is one of the features that make it such a powerful tool. We can imagine leveraging Elixir's ability to handle distributed computing to run concurrent background jobs, to support high-performance applications, to run expensive operations, you name it. This lesson gives us a basic introduction to the concept of distribution in Elixir and gives you the tools you need to start building distributed applications. By using supervised tasks, you can send messages across the various nodes of a distributed application. Metaprogramming. Metaprogramming is the process of using code to write code. In Elixir, this gives us the ability to extend the language to fit our needs and dynamically change the code. We'll start by looking at how Elixir is represented under the hood, then how to modify it, and finally we can use this knowledge to extend it. A word of caution: metaprogramming is tricky and should only be used when necessary. Overuse will almost certainly lead to complex code that is difficult to understand and debug. Quote: the first step to metaprogramming is to understand how expressions are represented. In Elixir, the abstract syntax tree, AST, the internal representation of our code, is composed of tuples. These tuples contain 3 parts: function name, metadata, and function arguments. In order to see these internal structures, Elixir supplies us with the quote_to function. Using quote_to, we can convert Elixir code into its underlying representation. Quote do 42, literals are only literals. Quote do 1 plus 2, we have the plus context Elixir and import kernel and arguments 1, 2. And then we quote an if statement, which will then have children where the value and the do true, else false. Notice the first 3 don't return tuples. There are 5 literals that return themselves when quoted: atom, string, all numbers, lists, and 2 element tuples. Unquote. Now that we can retrieve the internal structure of our code, how do we modify it? To inject new code or values, we use unquote 1. When we unquote an expression, it will be evaluated and injected into the AST. To demonstrate unquote 1, let's look at some examples. Quote divide 42 by denominator. Quote do so unquote is the interpolation. It's like we're injecting it. In the first example, our variable denominator is quoted, so the resulting AST includes a tuple for accessing the variable. In the unquote 1 example, the resulting code includes the value of denominator instead. Macros. Once we understand quote 2 and unquote 1, we're ready to dive into macros. It is important to remember that macros, like all metaprogramming, should be used sparingly. In the simplest of terms, macros are special functions designed to return a quoted expression that will be inserted into our application code. Imagine the macro being replaced with the quoted expression rather than called like a function. With macros, we have everything necessary to extend Elixir and dynamically add code to our applications. We begin by defining a macro using def macro2, which like much of Elixir, is itself a macro. As an example, we'll implement unless as a macro. Remember that our macro needs to return a quoted expression. So def macro unless expression do block do quote, if not unquote expression do unquote block. Let's require our module and give our macro a whirl. Require our module unless true high. Because macros replace code in our application, we can control when and what is compiled. An example of this can be found in the logger module. When logging is disabled, no code is injected, and the resulting application contains no references or function calls to logging. This is different from other languages where there is still the overhead of a function call even when the implementation is a no-op. To demonstrate this, we'll make a simple logger that can either be enabled or disabled. If application.getenv logger enabled, do quote do IOPuts logged message unquote message. Require logger def test. With logging enabled, our test function would result in code looking something like this. If we disable logging, the resulting code would be def test empty. Debugging. Okay, right now we know how to use quote 2, unquote 1, and write macros. But what if you have a huge chunk of quoted code and want to understand it? In this case, you can use macro toString2. Take a look at this example. Macro toString quote do foo.bar 1, 2, 3. Well, that wasn't very helpful. When you want to look at the code generated by macros, you can combine them with macro expand 2 and macro expand once 2. These functions expand macros into their given quoted code. The first may expand it several times, while the latter only once. For example, let's modify unless example from the previous section. So we require our macro and quote. If we send in quoted to macro expand once, and then toString it and puts that. So an instantiation of a macro. If we run the same code with macro expand 2, it's intriguing. It's probably expanding the if as well. Expands all the things, not just the unless. I wonder if they're... It's neat to know that the if comes out to this. You may recall that we've mentioned if is a macro in Elixir. Here we see it expanded into the underlying case statement. Private macros. Though not as common, Elixir does support private macros. A private macro is defined with def macro p and can be called from the module in which it was defined. Private macros must be defined before the code that invokes them. Macro hygiene. How macros interact with the caller's context when expanded is known as macro hygiene. By default, macros in Elixir are hygienic and will not conflict with our context. Def macro hygienic to value equals -1. Require example val is 42. Example.hygienic val. It doesn't override the outer, the existing val. What if we wanted to manipulate the value of val? To mark a variable as being unhygienic, we can use var bang 2. Let's update our example to include another macro utilizing var bang2. So if we wrap the variable val in var bang, then it will, yep. By including var bang2 in our macro, we manipulated the value of val without passing it into our macro. The use of non-hygienic macros should be kept to a minimum. By including var bang2, we increase the risk of a variable resolution conflict. Binding. We already covered the usefulness of "1", but there's another way to inject values into our code: binding. With variable binding, we are able to include multiple variables in our macro and ensure they're only unquoted once, avoiding accidental revaluations. To use bound variables, we need to pass a keyword list to the bind quoted option in quote 2. To see the benefit of bind quote and to demonstrate the reevaluation issue, let's use an example. We can start by creating a macro that simply outputs the expression twice. Def macro double puts expression quote, outputs unquote expression unquote expression. We'll try out our new macro by passing it to the current system time. We should expect to see it output twice. Example.double puts OS system time. The times are different. What happened? Using unquote 1 on the same expression multiple times results in reevaluation, and that can have unintended consequences. Let's update the example to use bind quoted and see what we get. Quote, bind quoted, expression. Now we get the same system time. With bind quoted, we get our expected outcome, the same time printed twice. Now that we've covered quote 2, unquote 1, and def macro 2, we have all the tools necessary to extend Elixir to suit our needs. Umbrella projects. Sometimes a project can get big, really big in fact. The mix build tool allows us to split our code into multiple apps and make our Elixir projects more manageable as they grow. Introduction. To create an umbrella project, we start a project as if we're going to start a normal mix project, but pass the umbrella flag. For this example, we are going to make the shell a machine learning kit. We're going to make the shell of a machine learning toolkit. Why a machine learning toolkit? Why not? It is made up of various learning algorithms and utility functions. Mix new machine learning toolkit -- umbrella. Your umbrella project was created successfully. Inside your project, you will find an apps directory where you can create and host many apps. As you can see from the shell command, Mix created a small skeleton project for us with two directories: apps, where our sub-child projects will reside, and config, where our umbrella project's configuration will live. Child projects. Let's change into the project's Machine Learning Toolkit apps directory and create 3 normal applications using Mix as so: Mix new utilities, Mix new datasets, and Mix new SVM. We should now have a project tree like so. If we change back to the umbrella project's root, we can see that we can call all the typical commands such as compile. As the subprojects are just normal applications, you can change into their directories and do all the same stuff as usual that Mix enables you to do. IEX. You may think that interacting with apps would be a little different in an umbrella project. Well, believe it or not, you would be wrong. If we change directory into the top level directory and start an IEX with the IEX capital S mix, we can interact with all the projects normally. Let's alter the contents of apps datasets lib datasets.ex for this simple example. So we have a hello from the datasets.hello. We start up an IEX mix session. And we do that from the root. I think. That's cool. Specifications and types. Give me a second, I'll be right back. Alright, back. Specifications and types. In this lesson, we'll learn about @spec and @type syntax. @spec is more of a syntax complement for writing documentation that can be analyzed by tools. @type helps us write more readable and easier to understand code. Introduction. It's not uncommon you would like to describe the interface of your function. You can use @doc annotation, but it is only information for other developers that is not checked at compilation time. For this purpose, Elixir has @spec annotation to describe the specification of a function that will be checked by the compiler. However, in some cases, specification is going to be quite big and complicated. If you would like to reduce complexity, you want to introduce a custom type definition. Elixir has the @type annotation for that. On the other hand, Elixir is still a dynamic language. That means all information about a type will be ignored by the compiler, but it could be used by other tools. Specification. If you have experience with Java or Ruby, you can think about specification as an interface. Specification defines what should be the type of a function's parameters and of its return value. To define input and output types, we use the @spec directive placed right before the function definition and taking as a params the name of the function, a list of parameter types, and after a double colon, the type of the return value. Let's take a look at an example. So we have a or a sum product function that takes a single argument, a single parameter, and returns an integer. So before it we have a spec, sum product, integer, and it returns an integer. Everything looks okay, and when we call it, a valid result will be returned. But the function sum returns a number, not an integer, as we expected in spec. It could be a source of bugs. There are tools like Dialyzer to perform static analysis of code that helps us find this type of bug. We'll talk about them in another lesson. Custom types. Writing specifications is nice, but sometimes our functions work with more complex data structures than simple numbers or collections. In that definition's case in spec, it could be hard to understand and or change for other developers. Sometimes functions need to take in a large number of parameters or return complex data. A long parameter list is one of many potential bad smells in one's code. In object-oriented languages like Ruby or Java, we could easily define classes to help solve this problem. Elixir does not have classes, but because it is easy to extend, we can define our own types. Out of the box, Elixir contains some basic types like integer or PID. Defining custom type. Let's modify our sum times function and introduce some extra params. I like examples. That's nice. We introduced a struct in the examples module that contains two fields, first and last. This is a simpler version of the struct from the range module. For more information on structs, reference the section on modules. Let's imagine that we need a specification with an example struct in many places. It would be annoying to write long, complex specifications and could be a source of bugs. A solution to this problem is add type. Elixir has 3 directives for types. Add type, which is a simple public type. Internal structure of a type is public. Add type P, type is private and could be used only in the module where it is defined. And then add opaque, type is public, but internal structure is private. Let's define our type. So in our def modules example, we have a def struct first nil, last nil, and at type t first last double colon examples first last type t double colon examples first integer last integer. We define the type t first last already, which is a representation of the struct examples first last last. At this point, we see types could take parameters, but we defined type t as well, and this time it is a representation of the struct. examples first integer, last integer. What's the difference? The first one represents the struct examples in which the two keys could be any type. The second one represents the struct in which the keys are integers. This means that code which looks like this, examples.t, string.t, is equal to code like documentation of types. The last thing that we need to talk about is how to document our types. As we all know from the documentation lesson, we have @doc and @module_doc annotations to create documentation for function and modules. For documentation types, for documenting our types, we can use @typedoc. So we have a typedoc type that represents examples struct with first as integer and last as integer. The directive typedoc is similar to @doc and module_doc. Behaviors. We learned about type specs in the previous lesson. Here we'll learn how to require a module to implement those specifications. In Elixir, this functionality is referred to as behaviors. Uses. Sometimes you want modules to share a public API. The solution for this in Elixir is behaviors. Behaviors perform two primary roles. First, defining a set of functions that must be implemented, and second, checking whether that set was actually implemented. Elixir uses a number of behaviors such as GenServer, but in this lesson we'll focus on creating our own instead. Defining a behavior. To better understand behaviors, let's implement one for our worker module. These workers will be expected to implement two functions, init1 and perform2. In order to accomplish this, we'll use the @callback directive with similar syntax to @spec. This defines a required function. For macros, we can use @macroCallback. Let's specify the init1 and perform2 functions for our workers. So we have a callback init that is a state in a term, and it returns then a tuple of OK, new state term, or error and reason term. Then a callback perform args term, state term, which returns an OK with a result term and a new state, or an error and a reason term and a new state. Here we've defined init1 as accepting any value and returning a tuple of either OK state or error reason. This is a pretty standard initialization. Our perform2 function will receive some arguments for the worker along with the state we initialized. We'll expect perform2 to return OK result state or error reason state, much like GenServers. Using behaviors. Now that we've defined our behaviors, we can use it to create a variety of modules that all share the same public API. Adding a behavior to our module is easy with the @behavior attribute. Using our new behavior, let's create a module whose task will be downloading a remote file and saving it locally. @behavior worker. So we have init, perform, http poison get this and get the body and then write file. This write file. Spawned. Or how about a worker that compresses an array of files? That's possible too. And there's a lot of useful examples in here. While the work performed is different, the public-facing API isn't, and any code leveraging these modules can interact with them, knowing they'll respond as expected. This gives us the ability to create any number of workers, all performing different tasks, but conforming to the same public API. If we happen to add a behavior but fail to implement all of the required functions, a compile time warning will be raised. To see this in action, let's modify our example compressor code by removing the init1 function. Now when we compile our code, we should see a warning. Warning, undefined behavior function init1 for behavior example worker. That's it. Now we're ready to build and share behavior with others. Gen stage. In this lesson, we're going to take a closer look at Gen stage, what role it serves, and how we can leverage it in our applications. Introduction. So what is Gen stage? From the official documentation, it is a specification and computational flow for Elixir. But what does that mean to us? What it means is that Gen stage provides a way for us to define a pipeline of work to be carried out by independent steps or stages in separate processes. If you've worked with pipelines before, then some of these concepts should be familiar. To better understand how this works, let's visualize a simple producer-consumer flow. A produces something that B consumes and then sends it on to C, which then consumes it. In this example, we have three stages: A producer, B, a producer-consumer, and C, a consumer. A produces a value which is consumed by B. B performs some work and returns a new value, which is received by our consumer C. The role of our stage is important, as we'll see in the next section. While our example is one-to-one producer to consumer, it's possible to both have multiple producers and multiple consumers at any stage. To better illustrate these concepts, we'll be constructing a pipeline with GenStage. But first, let's explore the roles that GenStage relies upon a bit further. Consumers and producers. As we've read, the role we give our stage is important. The GenStage specification recognizes three roles: producer, a source. Producers wait for demand from consumers and respond with requested events. Producer-consumer, both a source and a sink. Producer consumers can respond to demand from other consumers as well as request events from producers. Consumer, a sink. A consumer requests and receives data from producers. Notice that our producers wait for demand. With GenStage, our consumers send demand upstream and process data from our producer. This facilitates a mechanism known as back pressure. Back pressure puts the onus on the producer to not overpressure when consumers are busy. Now that we've covered the roles within GenStage, let's start on our application. Getting started. In this example, we'll be constructing a GenStage application that emits numbers, sorts out the even numbers, and finally prints them. For our application, we'll use all three GenStage roles. Our producer will be responsible for counting and emitting numbers. We'll use a producer-consumer to filter out only the even numbers and later respond to demand from downstream. Last, we'll build a consumer to display the remaining numbers for us. We'll begin by generating a project with a supervision tree. Mix, new, GenStage example, the supervision tree. Let's update our dependencies in mix.exs to include GenStage. We should fetch the dependencies and compile before we go much further. Mix, depth-get, and then compile. Oh, that's cool. Now we're ready to build our producer. The first step of our GenStage application is creating our producer. As we discussed before, we want to create a producer that emits a constant stream of numbers. Let's create our producer file. So we make a directory called GenStage example inside lib, and then we make a producer file there. Now we can add the code. So we use GenStage. We have a start link and a init. Then we also have a handle demand. We have this inside start link. We forward on to GenStage start link. Init. Producer counter to list. The two most important parts to take note of here are init1 and handle demand 2. Then in init1, we set the initial state as we've done in our gen servers. But more importantly, we label ourselves as a producer. The response from our init function is what GenStage relies upon to classify our process. The handle demand 2 function is where the majority of our producer is defined. It must be implemented by all GenStage producers. Here we return the set of numbers demanded by our consumers and increment our counter. The demand from consumers, demand, in our code above, is represented as an integer corresponding to the number of events they can handle. It defaults to 1000. Producer consumer. Now that we have a number generating producer, let's move on to our producer consumer. We want to request numbers from our producer, filter out the odd ones, and respond to demand. So we make a producer consumer file, and we add a similar setup. Now we're requiring integer. State doesn't matter. Init, and we return producer consumer state and subscribe to the producer that we just created. And then we have a handle events, whereas we had a handle demand in the producer. Handle events. Is there also a handle demand? Handle events. Filter is even. No reply, numbers state. You may have noticed with our producer consumer, we've introduced a new option in init1 and a new function handle events 3. With the subscribe to option, we instruct GenStage to put us into communication with a specific producer. The handle events 3 function is our workhorse, where we receive our incoming events, process them, and return our transform set. As we'll see, consumers are implemented in the same way, But the important difference is what our handle events 3 function returns and how it is used. When we label our process as a producer-consumer, the second argument of our tuple, numbers in this case, is used to meet the demand of consumers downstream. When we label our second argument of our tuple, numbers, in our case, is used to meet the demand of consumers downstream. In consumers, this value is discarded. Consumer. Last but not least, we have our consumer. Let's get started. So we make a consumer file. Since consumers and producer consumers are so similar, our code won't look much different. So we use GenStage, start link module, state doesn't matter, init consumer, subscribe to the producer consumer. Then we handle events from state, and then for event in events, inspect self event state. As a consumer, we never emit events. As we covered in the previous section, our consumer does not emit events, so the second value in our tuple will be discarded. Putting it all together, now that we have our producer, consumer, and consumer built, we're ready to wire everything together. Let's start by opening our lib genstage example application.ex and adding our new processes to the supervision tree. Initial state. If things are all correct, we can run our project and we should see everything working. Mix run, no halt. We did it. As we expected, our application only emits even numbers, and it does so quickly. At this point, we have a working pipeline. There is a producer emitting numbers, a producer consumer discarding odd numbers, and a consumer displaying all of this and continuing the flow. Multiple producers or consumers. We mentioned in the introduction that it was possible to have more than one producer or consumer. Let's take a look at just that. If we examine the IO inspect output from our example, we'll see that every event is handled by a single PID. Let's make some adjustments for multiple workers by modifying the application EX. So now we have 2 consumers. We specify a D for each. Now that we've configured 2 consumers, let's see what we get if we run our application now. As you can see, we now have multiple PIDs by simply adding a line of code and giving our consumers IDs. Use cases. Now that we've covered GenStage and built our first example application, what are some of the real use cases for GenStage? Data transformation pipeline. Producers don't have to be simple number generators. We could produce events from a database or even another source like Apache's Kafka. With a combination of producer consumers and consumers, we could process, sort, catalog, and store metrics as they become available. Work queue. Since events can be anything, we could produce works of unit. Units of work to be completed by a series of consumers. Event processing. Similar to a data pipeline, we could receive, process, sort, and take action on events emitted in real time from our sources. There are just these are just a few of the possibilities for Gen stage. Protocols. In this lesson, we're going to look at protocols, what they are, and how to use them in Elixir. What are protocols? So what are they? Protocols are a means of achieving polymorphism in Elixir. One pane of Erlang is extending an existing API for newly defined types. To avoid this in Elixir, the function is dispatched dynamically based on the values type. Elixir comes with a number of protocols built in. For example, the string.chars protocol is responsible for the toString1 function we've seen used previously. Let's take a closer look at toString1 with a quick example. So we have a toString5, toString 12.4, and a toString foo. As you can see, we've called the function on multiple items and demonstrated that it works on all of them. What if we call toString1 on tuples or any type that has an implemented string chars? Let's see. Protocol string chars not implemented for foo. As you can see, we get a protocol error as there is no implementation for tuples. In the next section, we'll implement the string chars protocol for tuples. Implementing a protocol. We saw that toString1 has not been implemented for tuples, so let's add it. To create an implementation, we'll use defimpl with our protocol and provide the for option and our type. Let's take a look at how it might look. So defimpl string chars for tuple. Do def toString tuple interior. We grab the interior and then we map that interior to string, and then we join it with a comma. If we copy this into IEX, we should now be able to call toString1 on a tuple without getting an error. Oh man. We know how to implement a protocol, but how do we define a new one? For our example, we'll implement toAtom. Let's see how to do that with def protocol. So def protocol as atom to def toAtom data. Then let's make an implementation for atom, byte string, list, and map. And for atom, we simply return itself. For string, to delegate, def delegate. For bit string, def delegate to list. And for map, we get the list first. We get the first map key. Here we've defined our protocol and expected function toAtom1 along with implementations for a few types. Now that we have our protocol, let's put it to use in IEX. Import as atom, toAtom string with string, and atom returns itself. A list. That's kind of weird, but toAtom, and then the first key in the map. It is worth to note that although underneath structs are maps, they do not share protocol implementation with maps. They are not enumerable. They cannot be accessed. As we can see, protocols are a powerful way to achieve polymorphism. Why are you whispering? Uh, this, this is kind of how I talk in the morning. I don't know. Yeah. I have a roommate, but I mean, he's 2 rooms over. I don't know. Yeah, just don't speak loudly. Let's see. Ecto. And this is Elixir School, which is a programming language. So, Ecto. Ecto is an official Elixir project providing a database wrapper and integrated query language. With Ecto, we're able to create migrations, define schemas, and insert and update records and query them. Adapters. Ecto supports different databases through the use of adapters. A few examples of adapters are PostgreSQL, MySQL, and SQLite. For this lesson, we'll configure Ecto to use the PostgreSQL adapter. Getting started. Through the course of this lesson, we'll cover 3 parts of Ecto. The repository provides the interface to our database, including the connection. Migrations, a mechanism to create, modify, and destroy database tables and indexes. Schemas, specialized structs that represent database table entries. To start, we'll create an application with a supervisor tree. So mix new friends with a supervision tree, and then add Ecto and Postgres package dependencies in your mix.exs file. And then fetch the dependencies using mix deps-get. Then create the repository. A repository in Ecto maps to a data store such as our Postgres database. All communication to the database will be done using this repository. Set up a repository by running mix ecto.gen.repo-r example.repo. This will generate the configuration required in config.exs to connect to a database, including the adapter to use. This is the configuration file for our example application. So we have config, our application, example repo, adapter is the Postgres adapter, database friends_repo, username password blank, host localhost. This configures how Ecto will connect to the database. Note how we chose the Ecto adapter's Postgres adapter. It also creates an example repo module inside libfriendsrepo.ex. So we have this def module example.repo, use ecto.repo, and the OTP app is friends. We'll use the example repo module to query the database. We'll also tell this module to find its database configuration information in the Friends Elixir application. Next, we'll set up the example repo as a supervisor within our application supervision tree in application.ex. This will start the Ecto process when our application starts. After that, we'll need to add the following line in our config.exs. Ecto repos, then this repo. This will allow our application to run Ecto mix commands from the command line. We're all done configuring the repository. We can now create the database inside of Postgres with this command: mix ecto create. Ecto will use the information in config/config.exs file to determine how to connect to Postgres and what name to give the database. If you receive any errors, make sure the configuration information is correct and that your instance of Postgres is running. Migrations. To create and modify tables inside the Postgres database, Elixir provides us with migrations. Each migration describes a set of actions to be performed on our database, like which tables to create or update. Since our database doesn't have any tables yet, we'll need to create a migration to add some. The convention in Ecto is to pluralize our tables, so for our application, we'll need a people table. So let's start there with our migrations. The best way to create migration is the mix ecto.gen.migration name task. So in our case, let's use mix.ecto.gen.migration create people. This will generate a new file in the priv repo migrations folder containing timestamp in the file name. If we navigate to our directory and open the migration, we should see something like this. So def module example.repo.migrations.create people. Use ecto migration, and then it has a change or a def up and down. Let's start by modifying the change 0 function to create a new table, people, with name and age. Create table, people, add name, string, null false, add age, integer, default 0. We can see above, we've also defined the column's data type. Additionally, we've included null, false, and default 0 as options. Let's jump to the shell and run our migration. Mix ecto.migrate. Schemas. Now that we've created our initial table, we need to tell Ecto more about it. Part of how we do that is through schemas. A schema is a module that defines mappings to the underlying database table fields. While Ecto favors pluralization of database table names, the schema is typically singular, so we'll create a person schema to accompany our table. Let's create our new schema at libfriendsperson.ex. Def module example.person. Use ecto.schema, then schema people, field, name, string, field, age, integer, default 0. Here we can see that the example person module tells Ecto that this schema relates to the people table, and that we have two columns, name, which is a string, and age, an integer with a default of 0. Let's take a peek at our schema by opening IEX and creating a new person. So an example person, default 0. As expected, we get a new person with the default value applied to age. Now let's create a real person. Since schemas are just structs, we can interact with our data like we're used to. Map get person name. Pattern matching. Similarly, we can update our schema just as we would any other map or struct in Elixir. Set his age to 18. Change his name to Jerry. In our next lesson on change sets, we'll look at how to validate data changes, and finally how to persist them to our database. Yeah, I mean, kind of close. Just my closet's pretty big. Change sets. In order to insert, update, or delete data from the database, ecto repo insert2 update to, and delete to require a change set as their first parameter. But what exactly are change sets? A familiar task for almost every developer is checking input for potential errors. We want to make sure that data is in the right state before we attempt to use it for our purposes. Ecto provides a complete solution for working with data changes in the form of the change set module and data structure. In this lesson, we're going to explore this functionality and learn how to verify data's integrity before we persist it to the database. Creating your first change set. Let's look at an empty change set struct. Looks like it has an action, changes, errors, data, valid. As you can see, it has some potentially useful fields, but they are all empty. For a change set to be truly useful, when we create it, we need to provide a blueprint of what the data is like. What better blueprint for our data than the schemas we've created that define our fields and types? Let's see a common user schema. So we have a field name string. To create a change set using the user schema, we're going to use ecto change set cast for. Ecto change set cast. Then we send in a user struct, something here, and then name. Valid true. The first parameter is the original data, an empty user struct in this case. Ecto is smart enough to find the schema based on the struct itself. Second in order are the changes we want to make, just an empty map. The third parameter is what makes cast for special. It is a list of fields allowed to go through, which gives us the ability to control what fields can be changed and safeguard the rest. You can see how the new name was ignored the second time, where it was not explicitly allowed. An alternative to cast for is the change to function, which doesn't have the ability to filter changes like cast for. It is useful when you trust the source making the changes or when you work with the data manually. Now we can create change sets, but since we do not have validation, any changes to our user's name will be accepted, so we could end up with an empty name. Ecto says the change set is valid, but actually, we do not want to allow empty names. Let's fix this. Validations. Ecto comes with a number of built-in validation functions to help us. We're going to use ecto change set a lot, so let's import ecto change set into our user.ex module, which contains our schema. Now we can use the cast for function directly. It is common to have one or more change set creator functions for a schema. Let's make one that accepts a struct, a map of changes, and returns a change set. Now we can ensure that name is always present with validate required. When we call the user change set to function and pass an empty name, the change set will no longer be valid and even contain a helpful error message. Note, do not forget to run recompile when working in IEX, otherwise it won't pick up the changes you make in code. If you attempt to do repo.insert change set with the change set above, you will receive error change set tuple back with the same error, so you do not have to check change set valid yourself every time. It is easier to attempt performing insert, update, or delete and process the error after there is one. Apart from validate required 2, there's also validate length 3, which takes some extra options. So now we also validate that the name is at least 2 characters long. You can try and guess what the result would be if we passed a name that consists of a single character. Errors. Name should be at least 2 characters. You may be surprised that the error message contains the cryptic count. This is to aid translation to other languages. If you want to display the errors to the user directly, you can make them human readable using traverse errors too. Take a look at the example provided in the docs link. Some of the other built-in validators in Ecto ChangeSet are validate acceptance 3, validate change 3 and 4, validate confirmation 3, validate exclusion and validate inclusion 4, validate format 4, validate number 3, validate subset 4. You can find the full list with details and how to use them here. Custom validations. Although the built-in validators cover a wide range of use cases, you may still need something different. Every validate underscore function we have used so far accepts and returns an Ecto ChangeSet, so we can easily plug our own. For example, we can make sure that only fictional character names are allowed. Fictional names: Black Panther, Wonder Woman, Spider-Man. Validate fictional name. Takes a ChangeSet. Otherwise, we add an error. Name is not a superhero. Above, we introduced 2 new helper functions: getFilled 3 and addError 4. What they do is almost self-explanatory, but I encourage you to check the links to the documentation. Oh, they are links. It is a good practice to always return an Ecto ChangeSet, so you can use the pipe operator and make it easy to add more validations later. Great, it works. However, there was really no need to implement this function ourselves. The validate inclusive for function could be used instead. Still, you can see how you can add your own errors, which should come useful. Adding changes programmatically. Sometimes you want to introduce changes to a change set manually. The put change 3 helper exists for this purpose. Rather than making the name field required, let's allow users to sign up without a name and call them anonymous. The function we need will look familiar. It accepts and returns a change set, just like the validate fictional name one we introduced earlier. Set name if anonymous, change set. Put change set name anonymous if the name is nil. We can set the user's name to anonymous only when they register in our application. To do this, we're going to create a new change set creator function. Registration change set struct cast params name set name if anonymous. Now we don't have to pass a name. A name and anonymous will be automatically set as expected. Having change set creator functions that have a specific responsibility, like registration change set to, is not uncommon. Sometimes you need the flexibility to perform only certain validations or filter specific parameters. The function above could be then used in a dedicated signup1 helper elsewhere. Conclusion. There are a lot of use cases and functionality that we did not cover in this lesson, such as schemaless change sets that you can use to validate any data, or dealing with this with side effects alongside the change set, prepare changes to, or working with associations and embeds. We may cover these in a future advanced lesson, but in the meantime, we encourage you to explore Ecto's change sets documentation for more information. Associations. In this section, we'll learn how to use Ecto to define and work with associations between our schemas. Setup. We'll be building off the app example from the previous lessons. Types of associations. There are 3 types of associations we can define between our schemas. We'll look at what they are and how to implement each type of relationship. First, there's belongs to / has many. We're adding some new entities to our example app's domain model so they can catalog our favorite films. We'll start with 2 schemas, movie and character. We'll implement a has many belongs to relationship between these 2 schemas. A movie has many characters and a character belongs to a movie. The has many migration. Let's generate a migration for movie. Mix, ecto, gen, migration, create movies. Open up the newly created migration file and define your change function to create the movies table with a few attributes. So we have a title and a tagline within our table movies. And then we're going to make a movie module and use ecto schema and define the same fields that we just added. But we also we'll add a schema that specifies the has many relationship between movies and its characters. The has many 3 macro doesn't add anything to the database itself. What it does is use the foreign key on the associated schema characters to make a movie's associated characters available. This is what will allow us to call movie.characters. The belongs to migration. Now we're ready to build our character migration in schema. A character belongs to a movie, so we'll define a migration and a schema that specifies this relationship. First, generate the migration. Mix, ecto, gen, migration, create characters. To declare that a character belongs to a movie, we need the characters table to have a movie_ID column. We want this column to function as a foreign key. We can accomplish this with the following line in our create table function. Add movie ID references movies. So our migration should look like this. Create table characters has a name, and then also movie ID references movies. The belongs to schema. Our schema likewise needs to define the belongs to relationship between a character and its movies and its movie. So in addition to the name, we also have the belongs to movie and then the movie module. Let's take a closer look at what the belongs to 3 macro does for us. Unlike adding the movie ID column to our characters table, this macro doesn't add anything to the database. It does give us the ability to access our associated movies schema through characters. It uses the foreign key of movie ID on the characters table to make the character's associated movie available when we query for characters. This is what will allow us to call character.movie. Now we're ready to run our migrations. Mix ecto.migrate. Belongs to has 1. Let's say that a movie has 1 distributor. For example, Netflix is the distributor of their original film Bright. we'll define the distributor migration and schema with the belongs to relationship. Let's generate the migration. So we created a migration called create distributors. Our migration should add a foreign key of module or of movie ID to the distributors table. So we have this references movies, and the distributor schema should use the belongs to 3 macro to allow us to call distributor.movie and look up a distributor's associated movie using this foreign key. So we add that here. Next up, we'll add the has1 relationship to the movie schema. Has1 distributor, example, distributor. The has1 3 macro functions just like the hasMany 3 macro. It doesn't add anything to the database, but it does use the associated schema's foreign key to look up and expose the movie's distributor. This will allow us to call movie.distributor. And we're ready to run migrations. Mix.ecto migrate or mix ecto migrate. Many to many. Let's say that a movie has many actors and that an actor can belong to more than one movie. We'll build a join table that references both movies and actors to implement this relationship. First, let's generate the actors migration. Generate migration, create actors. Here we only add the name string, and then let's create our join table, create movies, actors. We'll define our migration such that the table has 2 foreign keys. We'll also add a unique index to enforce unique pairings of actors and movies. Create unique index, movies, actors on the two fields. And we have 2 references, movies and actors. Next up, let's add the many-to-many macro to our movie schema. So as a many-to-many actors, example actor, join through movies actors. Finally, we'll define our actor schema, our actor schema with the same way many-to-many, with the same many-to-many macro. Many-to-many movies, movie, join through movies actors. And then we run migrations. Saving associated data. The manner in which we save records along with their associated data depends on the nature of the relationship between the records. Let's start with the belongs to has many relationship. Saving with ecto build association or build assoc 3. With a belongs to relationship, we can leverage ecto's build assoc 3 function. Build assoc takes 3 arguments: the struct of the record we want to save, the name of the association, and any attributes we want to assign to the associated record we are saving. Let's save a movie and an associated character. First, we'll create a movie record. So I bring in some stuff, and then we have a movie, Ready Player One, with a tagline, something about video games. Then we have this change set, or no, yeah? And then we insert that change set. Now we'll build our associated character and insert it into the database. So now we ecto build association movie characters, and we're adding this one. Notice that since the movie schema has many macro specifies that a movie has many characters, the name of the association we pass in as a second argument to build associate 3 is exactly that, characters. We can see that we've created a character that has its movie ID properly set to the ID of the associated movie. In order to use build assoc 3 to save a movie's associated distributor, we take the same approach of passing the name of the movie's relationship to distributor as the second argument to build assoc3. Distributor. Many to many. Saving with ecto change set put assoc4. The build assoc3 approach won't work for our many to many relationship. That is because neither the movie nor actor tables contain a foreign key. Instead, we need to leverage ecto change sets and the put association for function. Assuming we already have the movie record we created above, let's create an actor record. So we create actor record, and we insert that into the database. Now we're ready to associate our movie to our actor via the join table. Note that in order to work with change sets, we need to make sure that our movie record has preloaded its associations, its associated schemas. We'll talk more about preloading in a bit. For now, it's enough to understand that we can preload our associations like this. Movie, repo, preload, movie, and then the associations we want to preload. Next up, we'll create a change set for our movie record. So we make a change set for the movie. Now we'll pass our change set as the first argument to ecto change set put assoc4. Movie change set. And then we put association actors. And we add this actor. This gives us a new change set that represents the following change. Add the actors in the list of actors to give movie record. Add the actors in this list of actors to the given movie record. Lastly, we'll update the given movie and actor records using our latest change set. Repo.update movie actors change set. We can see that this gives us a movie record with the new actor properly associated and already preloaded for us under movie.actors. We can use this same approach to create a brand new actor that is associated with the given movie. Instead of passing a saved actor struct into put assoc4, we can simply pass in an actor struct describing a new actor that we want to create. We can see that a new actor was created with an ID of 2, and the attributes were assigned to it. In the next section, we'll learn how to query for our associated records. Querying. In this lesson, we'll be building off the example app and the movie cataloging domain we set up in the previous lesson. Fetching records with ecto.echo.recto.repo. Recall that a repository in ecto maps to a data store such as our Postgres database. All communication to the database is done using this repository. We can perform simple queries directly against our example.repo with the help of a handful of functions. Fetching records by ID. We can use the repo get3 function to fetch a record from the database given its ID. This function requires 2 arguments, a queryable data structure and the ID of a record to retrieve from the database. It returns a struct describing the record found, if any. It returns nil if no such record is found. Let's take a look at an example. Below, we'll get the movie with an ID of 1. repo get movie 1. Notice that the first argument we give to repo.get3 is our movie module. Movie is queryable because the module uses the ecto.schema module and defines a schema for its data structure. This gives movie access to the ecto.queryable protocol. This protocol converts a data structure into an ecto query. Ecto queries are used to retrieve data from a repository. More on queries later. Fetching records by attribute. We can also fetch records that meet a given criteria with the repo get by 3 function. This function requires 2 arguments, the queryable data structure and the clause with which we want to query. Repo get by 3 returns a single result from the repository. Let's look at an example. Repo.getBy movie title Ready Player One. If we want to write more complex queries, or we want to return all records that meet a certain condition, we need to use the ecto.query module. Writing queries with ecto.query. The ecto.query module provides us with a query DSL, which we can use to write queries to retrieve data from the application's repository. Creating queries with ecto.query from to. We can create a query with the ecto.query from to function. This function takes 2 arguments, an expression and a keyword list. Let's create a query to select all the movies from our repository. So we import ecto.query, and then we have this query that is not executed yet. From M in movie, select M. In order to execute our query, we use repo all to function. This function takes in a required argument of a ecto query and returns all the records that meet the conditions of the query. So repo all query. Using from with keyword queries. The example above gives the from to an argument of a keyword query. When using from with a keyword query, the first argument can be one of 2 things. An in expression, example M in movie, or a module that implements the ecto queryable protocol, example movie. The second argument is our select query, or our select keyword query, using from with a query expression. When using from with a query expression, the first argument must be a value that implements the ecto query protocol, queryable protocol, example movie. The second argument is an expression. Let's take a look at an example. So we have a query and select movie M repo all query. You can use query expressions when you don't need an in statement, M in movie. You don't need an in statement when you don't need a reference to a data structure. Our example doesn't require a reference to the data structure. We're not, for example, selecting movies where a given condition is met. So there's no need to use in expressions and keyword queries. Using select expressions. We use the ecto query select 3 function to specify the select statement portion of our query. If we want to select only certain fields, we can specify those fields as a list of atoms or by referencing the struct's keys. Let's take a look at the first approach. So select title. Notice that we did not use an in expression for the first argument given to our from function. That is because we do not need to create a reference to our data structure in order to use a keyword list with select. This approach returns a struct with only the specified field title populated. The second approach behaves a little differently. This time, we do need to use an in expression. This is because we need to create a reference to our data structure in order to specify the title key of the movie struct. So we have a query from M in movie and then select M title. And it only returns this, not the... Notice that this approach to using select returns a list containing the selected values. Using where expressions. We can use where expressions to include where clauses in our queries. Multiple where expressions are combined into where and SQL statements. So query M in movies where M title equals Ready Player One. We can use where expressions together with select. Where title equals player one, select M tagline. Using where with interpolated values. In order to use interpolated values or Elixir expressions in our where clauses, we need to use the pin operator. This allows us to pin a value to a variable and refer to that pin value instead of rebinding that variable. Getting the first and last records. We can fetch the first or last records from our repository using the ecto.queryFirstTo and ecto.queryLastTo functions. First, we'll query expression using the first2 function. First movie. Then we'll pass our query to the repo12 function to get our result. Repo first, or movie first, and repo.1. The ecto.queryLast function is used in the same way. Querying for associated data. Preloading. In order to be able to access the associated records that the belongs to, has many, and has one macros exposed to us, we need to preload the associated schemas. Let's take a look to see what happens when we try to ask a movie for its associated actors. Movie.actors, not loaded association. We can't access those associated characters unless we preload them. There are a few different ways to preload our records in Ecto. Preloading with two queries. The following query will preload associated records in a separate query. Preload actors. We can see the above line of the code ran two database queries. One for all the movies, and another one for all the actors with the given movie IDs. Preloading with one query. We can cut down on our database queries with the following. Join A in association from M, actors, and preload. This allows us to execute just one database call. It also has the added benefit of allowing us to select and filter movies and associated actors in the same query. For example, this approach allows us to query for all movies where the associated actors meet certain conditions using a join statement, something like this. Let's get all the movies that have John Wayne as an actor. More on join statements in a bit. Preloading fetched records. We can also preload the associated schemas of records that have already been queried from the database. So if we do repo.preload of something that we've already gotten, and actors. Now we can ask a movie for its actors. Using join statements, we can execute queries that include join statements with the help of ecto query join 5. Join character on where. The on expression can also use a keyword list. In the example above, we are joining an ecto schema on an ecto schema M in movies in movie. We can also join on an ecto query. Let's say our movies table has a column stars, where we store the star rating of a film, a number 1 through 5. So we're going to join to this with this. The ecto query DSL is a powerful tool that provides us with everything we need to make even complex database queries. This introduction provides you with the basic building blocks to start querying. Plug. If you're familiar with Ruby, you can think of plug as rack with a splash of Sinatra. It provides a specification for web application components and adapters for web servers. While not part of Elixir core, Plug is an official Elixir project. In this lesson, we'll build a simple HTTP server from scratch using the Plug Cowboy Elixir library. Cowboy is a simple HTTP server for Erlang, and Plug will provide us with a connection adapter for that web server. After we set up a minimal web application, we'll learn about Plug's router and how to use multiple plugs in a single web app. Prereqs. You need Elixir 1.5 or higher and Mix installed already. We'll start by creating a new OTP project with a supervision tree. So Mix new example supervision tree. And we need our Elixir app to include a supervision tree because we need to use a supervisor to start up and run our Cowboy 2 server. Dependencies. Adding dependencies is a breeze with Mix. To use Plug as an adapter interface for the Cowboy 2 server, we need to install the Plug Cowboy package. Add the following to your mix.exx file. At the command line, run the following mix tasks to pull in these new dependencies. Mix steps to get. The plug specification. In order to begin creating plugs, we need to know and adhere to the plug spec. Thankfully for us, there are only 2 functions necessary, init1 and call2. Here's a simple plug that returns hello world. So we have our hello world plug, and we import plug.con. We have a init options, and it returns options. Then we have a call con, and then options, which are here ignored. Then we have this connection, put response, content type, text plain, and send response 200 hello world. Save the file to lib example hello world plug. The init option is used to initialize our plug's options. It is called by a supervision tree, which is explained in the next section. For now, it'll be an empty list that is ignored. The value returned from init1 will eventually be passed to call2 as its second argument. The call2 function is called for every new request that comes in from the web server, Cowboy. It receives a plug construct connection struct as its first argument and is expected to return a plug con connection struct. Configuring the project's application module. We need to tell our application to start up and supervise the Cowboy web server when the app starts up. We'll do so with the plug Cowboy child spec 1 function. This function expects three options: scheme, which is HTTP or HTTPS as an atom; plug, the plug module to be used as the interface for the web server. You can specify a module name like myplug or a tuple of the module name and options, myplug, plug options, where plug options gets passed into your plug module's init1 function. Options, the server options, should include the port number on which you want your server listening for requests. Our lib example application file should implement the child spec in its start2 function. Note, we do not have to call child spec here. This function will be called by the supervisor starting this process. We simply pass a tuple with the module we want the child spec built for, and then the three options needed. This starts up a Cowboy 2 server under our app supervision tree. It starts Cowboy running under the HTTP scheme. You can also specify HTTPS. On the given port, 8080, specifying the plug, Hello World plug, as the interface for any incoming web requests. Now we're ready to run our app and send it some requests. Notice that because we generated an OTP app with the sup flag, our example application will start up automatically thanks to the application function. In mix.exs, you should see the following. We're ready to try out this minimalistic plug-based web server. On the command line, run mix run no halt. Once everything is finished compiling and Invo starting application appears, open a browser to localhost 8080 and it should display Hello World. Plug router. For most applications, like a website or a REST API, you want a router to route requests for different paths and HTTP verbs to different handlers. Plug provides a router to do that. As we are about to see, you don't need a framework like Sinatra in Elixir since we get that for free with Plug. To start, let's create a file at libexamplerouter.ex and copy the following into it. So we have this router module which uses plug router, then we plug match, plug dispatch, and we have this get base to say, hey, welcome, and anything else for a force. This is a bare minimum router with a code, but the code should be pretty self-explanatory. We've included some macros through use plug router and then set up two of the built-in plugs, match and dispatch. There are two defined routes, one for getting GET requests to the root and the second for matching all other requests so we can return a 404 message. Back in libexampleapplication.ex, we need to add example router into the web server supervision tree. Swap out the Hello World plug with the new router. Start the server again, stopping the previous one if it's running. Press Ctrl-C twice. Now in a web browser, go to localhost 8080 and it should output welcome. Then go to localhost 8080/Waldo or any other path, and it should output oops with a 404 response. Adding another plug. It is common to use more than one plug in a given web application, each of which is dedicated to its own responsibility. For example, we might have a plug that handles routing, a plug that handles incoming web requests, a plug that handles that authenticates incoming requests, etc. In this section, we'll define a plug to verify incoming request parameters, and we'll teach our application to use both of our plugs, the router and the validation plug. We create a plug that verifies whether or not the request has some set of required parameters. By implementing our validation in a plug, we can be assured that only valid requests will make it through our application. We will expect our plug to be initialized with two options, paths and fields. These represent the paths we apply our logic to and which fields to require. Note: plugs are applied to all requests, which is why we handle filtering requests and applying our logic to only a subset of them. To ignore a request, we simply pass the connection through. We'll start by looking at our finished plug and then discuss how it works. We create it in lib example plug verify request. So we have this module, then we define a module within that, incomplete request error raised when a required missing thing, root def exception message empty plug status 400. Init call the plug struct. Then we have this path. If path in ops paths do verify request with connection.params and ops.fields. This case contains fields in them all. The first thing to note is we have defined a new exception, incomplete request error, and that one of its options is plug status. When available, this option is used by plug to set the HTTP status code in the event of an exception. The second portion of our plug is the call to function. This is where we decide whether or not to apply our verification logic. Only when the request's path is contained in our paths option will we call verify request to. The last portion of our plug is a private function, verify request to, which verifies whether the required fields are present. In the event that some are missing, we raise incomplete request error. We've set up our plug to verify that all requests to upload include both content and MIME type. Only then will the route code be executed. Next, we need to tell the router about the new plug, edit the router and make the following changes. So we add this plug, parsers, URL encoded multi-part. Also bring in the verify request, plug verify request, fields, content, MIME type, path upload. With this code, we are telling our application to send incoming requests through the verify request plug before running through the code in our router via the function call. Plug verify request, fields, paths. We automatically invoke verify request init fields, content, MIME type, path, upload. This in turn passes the given options to the verify request call con ops function. Let's take a look at this plug in action. Go ahead and crash your local server. Remember, this is done by Control-C twice. Then restart the server, mix, run, no halt. Then go to the upload in your browser and you'll see that the page simply isn't working. We're not even getting our oops message. Now let's add our required params by going to upload, content, thing 1, MIME type, thing 2. Now we should see our uploaded message. It's not great that when we throw an error, we don't get any page, but we'll deal with how to handle errors with plugs later. Making the HTTP port configurable. Back when we defined the example module and application, the HTTP port was hard-coded in the module. It's considered good practice to make the port configurable by putting it in a configuration file. We'll set up an application environment variable in config/config exs. So we use mixconfig, and then we add a cowboy port 8080. Next, we need to update lib example application.ex to read the port configuration value and pass it to cowboy. We'll define a private function to wrap that responsibility. The third argument to application getenv is the default value for when the configuration directive is undefined. Now run our application, we can use mix run no halt. Testing a plug. Testing plugs is pretty straightforward thanks to plug test. It includes a number of convenience functions to make testing easy. Write the following test to test example router test. So we have this router test, use xunit case, use plug test, content, mime type, ops, router init, test, returns welcome to con equals con get this, assert that con state is sent, status at 200. Plug error handler. Notice earlier when we went to localhost upload, we don't even see an error page. Let's fix that by adding in a plug error handler. First, open up example router.ex and then write the following to that file. So now we use plug error handler and we handle errors, connection, kind, reason, stack, and we put a whole bunch of stuff, and then we send a response. Something went wrong. Notice at the top, we're now adding use plug error handler. This plug catches any error and then looks for a function handle errors to call. Handle errors just needs to accept the con as the first argument, and then a map with 3 items, kind, reason, and stack as the second. That's where we should be handling better errors, or better stack traces. You can see we've defined a very simple handle errors to see what's going on. Let's stop and restart our app again to see how this works. When you navigate to localhost upload, we see an error message, something went wrong. And when you look in the terminal, you'll see something like the following. This plug makes it really easy to catch the useful information needed for developers to fix issues, while being able to also give our end user a nice page so it doesn't look like our app totally blew up. You see a complete list of plugs here. Alright, I think that's all for me today. See ya.